Okay. Well, I guess I'll get started now. Welcome to the beginning of BSides Lisbon. I am Dan Guido, and I'm here to give first keynote in the red track. So if that's what you're here for, you made it to the right place. So I am flew in all the way from New York today to talk about the Smart Fuzzer Revolution. I wanted to try and put into context some of the research advances as well as some of the practical advances made in the state-of-the-art of automated bug finding of the last 2 years. I work in this field and I've been incredibly excited by this, and I want to share my excitement with all of you and show you not only how you can take advantage of this kind of new technology, but also how you can contribute to it. So I work at a company called Trail of Bits. I founded it a few years back. We specialize in research and development of technology like this. It really excites us to work in the most advanced parts of computer science and to merge that with computer security and to make it practical for people not only in government and research fields, but make it practical for people in commercial industry as well. So there's been a few blog posts that we've published where we've disclosed clients of ours like Facebook and Amazon, where we've worked on analysis tools that help them find bugs or help them secure their networks. But you can read more about us on our website if you're not familiar. So the agenda for today, I want to talk a little bit about the history, kind of where fuzzing came from, where automated bug finding techniques came from, what people have done in the past, and why what we're doing today is so much different. I'm going to discuss the current state of the art. The last 2 years, what has happened to really move the ball forward and make these techniques and make these techniques more accessible to regular developers, as well as make them significantly more effective than what came before it. And then finally, I'm going to talk about what problems lie ahead of us, because we are not there yet. We don't have the one true bug finding system that can just replace all of us with a machine. But we can get there. And there's a few different research roadblocks. There are funding roadblocks. There are organizational and developer roadblocks that we need to overcome that all of you can help me with in order to get there. So yeah, the summary here is we are in an automated software testing renaissance. It has never been better to work in this field than today. Okay, so smart fuzzing. I just need to define a term before we go on. Fuzzing is filled with all kinds of really opaque terms. Smart fuzzing, fuzzing is generally just trying random inputs, right? So smart fuzzing is, what if we analyze the program under test and instead of trying random inputs, we look at inputs that are likely to get new code coverage and otherwise touch more internal state in the program based on what we know about it. So smart fuzzing enables us to use an entirely new domain of knowledge to hyper-focus the activities that we undertake to test that program. Fuzzing deals with huge numbers of combinatorial state explosion. I'll put this on silent. And in order to deal with that, we need better techniques to narrow down that path, narrow down the number of inputs that we test to only the ones that actually get us code coverage, only the ones that let us explore new state. Smart fuzzing is how we get there. Okay, so history. In the beginning, right? 1998, fuzzing was sort of accidentally termed in a class assignment for an advanced operating systems course at the University of Washington. A professor asked his students to write a program that threw random input at other Unix command line utilities. Essentially what we're talking about here is just catting dev random into the program. We're not concerned with state, we're not concerned with structure, we're not concerned with whether the program even expects to get anything like what we're giving it. We're just flinging crap at it and hopefully it breaks. Surprisingly, that's a really effective strategy. That worked for about 10 years, and then people decided maybe we should improve upon this a little bit. And in the early 2000s, we started to see people come up with generational-based fuzzers, where we generate some kind of data structure that is what the program expects. And you see this occurring in parallel among a number of different research groups. People like the University of Oulu in Hawaii created Protoss, and Dave Eitel self-published his seminal paper on block-based fuzzing. which later made it into that great chapter in the Shellcoder's Handbook, and he built Spike. So these basically allow you to construct some kind of protocol or a file format using a BNF, and then annotate what types of data are expected in all those different fields, and then the fuzzer would make smart choices about what type of random data to put into those fields. And that was pretty good. At the same time, we also looked at mutation-based fuzzing. So this is really resource intensive, unlike, I guess generation is resource intensive as well. You have to sit there and create a spec in a BNF and like test it to make sure it's what the spec actually says. But with mutation, we're assembling a giant corpus of legitimate data. We're downloading all the PDFs on the internet, putting them into a giant directory, and then mutating and flipping all the bytes in them and running them through all the different PDF readers that we've got, right? That's mutation. That's going to find some bugs, but the only bugs it'll find are the ones that are exercised by the corpus that you generated, the corpus that you collected. And it's difficult to really guide a mutation-based fuzzer down certain paths in the program. You have to work with what you've got. So what's common to these, all of these, is that we're simply applying random mutations to well-formed inputs, except in the random case, I guess, to well-formed inputs and observing the results. We're just spending more time constructing what we're going to send to those programs, and then hopefully the program that is under test crashes more often. Now, along the way, there's been plenty of iterative advances. We've tried to improve upon this basic strategy in every way we can. We've created, we've measured code coverage and created minimum input sets. So instead of randomly running every PDF on the internet, we can use a tool that identifies which of them get you different kinds of code coverage and then eliminates the ones that are redundant from that test set. We can refuzz crashing inputs. This is what a friend of mine calls a rocket-propelled chainsaw. So once you find, I like that term too. Once you find a crash, once you find a valid crashing input, or rather an invalid crashing input, you can explore the state around it, explore the code around it by continuing to fuzz that crashing input. Generally, bugs cluster together, right? We can try to categorize crashes with heuristics, such as Microsoft's Bang Exploitable that was released many years ago, which some people love, some people hate, but regardless, it did advance the field a bit. And then back in 2005, 2006, the precursors to CLE came out, XE and Dart. They were some of the first attempts at combining concrete execution with symbolic execution and managing the state explosion through path pruning with STP. And then finally, we've got better SMT solvers than we had many years ago, like Z3, right? So these were all just iterative advances where we made some more progress on the general strategy of just taking well-formed inputs, mutating them, and then blindly observing the results. So in 2008, there is a clear delineation where dumb fuzzing ends and smart fuzzing begins. And that is delineated by something called SAGE that Microsoft made. I actually did not realize we'd be in a Microsoft building when I gave this talk. It stands for Scalable Automated Guided Execution. And it was published in a paper named Automated Whitebox Fuzz Testing. It's really one of the seminal works in this field. It's a fairly accessible paper if you want to go read it. I really appreciate them stating what they did so clearly. The key advance here is what they did is they combined fuzzing with symbolic execution to dynamically generate new tests while managing the state explosion problem. So there's 3 steps here, right? They run the program and trace it, and symbolically execute that trace, turn it into symbolic values to figure out what all the new constraints would be. What, this integer value needs to be above this in order to pass through this gate and reach this next basic block. Then they use a constraint solver to figure out what new inputs would satisfy those constraints so they can generate those new tests. And then they rank all the different new inputs that they've generated with the constraint solver to figure out which of them are actually going to be most effective at gaining the most code coverage. So the combination of these 2 techniques is that they can drill into a program significantly deeper with more precision than a random fuzzer would be able to. And SAGE was wildly used at Microsoft during the development cycle starting in, I think, Windows 7. Hugely successful tool. And some of the reasons it's successful are not what you would expect as a security researcher, right? So there's clear research advances here, We can do very advanced things compared to the fuzzers that came before it. We can overcome simple checksums, for instance, that would have stopped any fuzzer before it cold. But really, the key benefits with Sage was that it was easy to use and it was available. Microsoft made it work on binaries, so there wasn't source code. You didn't have to have a compilable set of source code in order to run it. You just gave it the output of whatever your dev cycle was. It worked on very large programs. You could run it on Microsoft Office, and it would actually complete in a reasonable amount of time. It would find real bugs. It doesn't require the developer to sit there and come up with a whole bunch of sample inputs to give them a whole bunch of sample document files. They could just start from nothing and find something. And then finally, when it actually did work, it found real bugs, and it gave you the inputs that caused those bugs, and they had some analysis around it so that the developer was sure that what they were fixing wasn't just a ghost in the, like a null reference or some kind of low-value code quality issue. It was a real security bug. And that's why Sage was really revolutionary, the combination of all these things. Now, at the same time, there's more development going on in the open. So Sage, not available outside Microsoft. AFL, open source. In comparison, AFL is not quite as smart. It doesn't use symbolic execution the way that Sage does, but it has the benefit of being incredibly simple to install and use for a bug finding tool. The key contribution for AFL is that they use compiler instrumentation to make programs easier to fuzz. That is really the key thing that AFL got right. It's also just a well-engineered piece of software. There's a lot of really common knowledge out there about how to construct a fuzzer, and Michal Zalewski packaged all of that up into a really nice, easy-to-use tool. It uses code coverage to guide fuzzing. It's somewhat fast, but easily parallelizable. And the most important thing is that developers use it, right? Unused tools don't find bugs. Kind of obvious. The proof here, they have a really nice little trophy case, I think they call it. This is as much as I could reasonably screenshot, but it goes on for many pages below this. I think there's one in here my intern found, my 16-year-old high school intern. Like, AFL is really easy to use. I can't stress that enough. But it's really attacked hard targets. This is kind of a testament to how we're really only at the beginning of the fuzzer kind of evolution here, where even a dumb fuzzer can find bugs in things like SQLite, in JavaScript core, in OpenSSL and OpenSSH. It's really, really impressive. So to recap, Sage is smart. It intelligently explores program paths, but you can't use it. AFL is dumb. You can use it, and it's still incredibly effective. It'll get stuck on the same kinds of things that all fuzzers will, like simple checksums. You just bang its head against the wall. So you've got a couple of different, from a research perspective here, which one is better? Like, can we create something that combines the best of both? Why do we have to be satisfied with simply, a dumb fuzzer, and how do we extract all of this incredible knowledge outside of Microsoft research and outside of Microsoft's development cycle into the real world? Not the real world, but the rest of the world. Note here on some terminology. At this point in the presentation, I start to flip a little bit from smart fuzzing to automated bug finding systems. I just consider automated bug finding to be a superset a little bit of smart fuzzing. So if that trips you up, that's what it means. So now, we're in about 2012, 2013, and DARPA has decided this is a problem they'd like to attack. This is a problem that they would like to fix. They're not satisfied with the status quo. They believe that the publicly available tools to automatically find bugs can be better, can integrate more of the currently available research that's out there. And they created a program called the Cyber Grand Challenge. The Cyber Grand Challenge is modeled based after the Capture the Flag contest that we're all familiar with, except instead of humans playing, there are only machines. The machines have to do everything a human would do in a Capture the Flag challenge. They have to receive pwnables, basically, and find vulnerabilities in them. Those vulnerabilities are called proof of vulnerability. It's a crashing input of some kinds, or it might be an input that gains some register control to demonstrate that there's some path towards exploitation for it. And it needs to fix that vulnerability. It needs to fix it in a performant way. It needs to, not slow down the program 100 times. It needs to keep its services up so that other competitors can still interrogate that service and collect flags from it if they have a valid exploit. The competition was measured by a fairly complex scoring algorithm that I'll get into a little bit later, but all the CRSs were given points the same way that a CTF competitor would, and the CRS with the most points would win the contest. Right, so that's the Cyber Grand Challenge in a nutshell. The really strange thing for me, and Trail of Bits was one of the competitors in this, was observing the converging strategies of all the teams that played. In the public presentations that every team has given since the Cyber Grand Challenge ended, which was at DEF CON this summer, you saw them all combine the same basic elements. You saw them combine fuzzing and symbolic execution in some way that they could communicate. Some of them sprinkled in other program analyses that were well known, nothing really revolutionary here. A lot of them tried to prioritize which inputs to test. All these different things. Everybody was concerned with resource control and allocation because the Cyber Grand Challenge scored you based on it. But the same general strategies for every single one. And you could prove this based on the outcome, based on the scores. When you looked at the score in the final event in that live YouTube stream that they had, everybody basically tracked very, very close to each other. The difference in points between first and seventh was really not substantial. Now, that's not to say it was kind of a failure. What we did find, though, is we found that we came up on several really difficult research problems that we don't have good solutions to. And these are all topics that you could spend ages working on. Things like, how do you efficiently mutate inputs? Not just in terms of selecting them, but what mutations to apply. All of these, every single one, could fill a PhD thesis. And I hope that some of these topics are explored after the contest has ended now. Now we kind of know what the limits are of applicable technology and like how far they get us. And we need to figure out the solutions to these problems to advance the state of the art again. So I mentioned that we competed in this challenge. Here is one of the solutions that we came up with. So we had a really difficult problem. We're a very small team. We're a commercial company. I have to pay salaries. I can't recruit a team of like 50 grad students that work for $500 a month. So we ended up having about 3, maybe sometimes 4 people working together on our team with no prior development that we could take advantage of. So we really leaned on open source technology, and we leaned on code bases like CLI, like a Python symbolic execution framework that we found on GitHub and then later hired the author of. We used tools like Redamza for input generation and wrapped it in our own dynamic binary tracing engine that we wrote. But these tools were not built to talk to each other. Most tools that security researchers build work in isolation. They silo their data, they produce some kind of output on the terminal, they don't accept all the same kinds of input. It's really difficult to strap all these tools together into an integrated system. So we found very quickly that the universal input that all of these programs take is input itself, the inputs to the program that it constructs. So we modified each of those programs, CLI, Python symbolic execution framework, various other tools that we use to test for bugs. And we collected all those inputs they generated, fed them back into a knowledge base, and then in that knowledge base, which we called minset, ranked them for the minimum set of maximal code coverage for those inputs, and used those to select which ones we would further test for. And then once that minset evaluated what the best ones were, it would actually share them with all the rest of the tools. That way, if a fuzzer got stuck on a checksum, it would give the best available input that it had back to minset, and minset might hand it off to a symbolic execution framework. And the symbolic execution framework would overcome the checksum, create a new valid input that gained more code coverage, send it back to minset, and then minset would send it to a fuzzer again. And now, magically, the fuzzer was able to overcome that code path that it was stuck on before. So this is kind of key to our strategy. It worked very well, but it's also very similar to the techniques that other teams came up with. So the benefits here, this challenge really, beyond constructing several practical tools that are now open source and identifying these research problems that we now must overcome to advance this field further, Cyber Grand Challenge was so effective because it got the right people in the room talking to each other. It got academics thinking about fuzzing again, where they thought this was a dead field. You don't see a huge amount of academic interest in fuzzing in many, many years. They've all moved on to symbolic execution and other kind of programming languages related topics, whereas fuzzing kind of just halted after the first initial attempts at publishing stuff. Security researchers never thought that academics could be practical. They didn't understand the value that certain new papers had presented, only until they were pressured inside of a contest to apply them and make them work to compete against other team members. And then none of these people actually knew how to create distributed systems that would work at scale to find real bugs. I think probably the biggest challenge for us going into this competition, because we have a mix of academics and security researchers at Trail of Bits, we did not have distributed systems expertise. And we definitely fell on our face pretty hard just trying to figure out EC2 and Docker and React and all the rest of these things that like regular developers understand very well. So most importantly, Cyber Grand Challenge advanced the state of the art in bug finding. Problems we thought were out of reach are now solved. And I'll give you one great example. So crackaddr. Crackaddr is a name for a very subtle vulnerability discovered in 2003 by Mark Dowd. The total sum of vulnerable code that we're talking about here is about 50 lines of code, but there is a state machine in it with so much hidden complexity that it is essentially impossible to find with purely static analysis. The path explosion problem is particularly acute with this piece of code. There are more atoms in the universe. There's more state in this 50 lines of code than there are atoms in the universe, which is insane. The effect, though, the impacts, and the reason why it's so important to find bugs like this is because the impact of this flaw is back in 2003, you could take over essentially every mail server in the world. So this is a cliff we need to scale in order to find bugs that are really important. We can't just let this be. So it's kind of been Everest for a lot of these automated tools. Here is a shamelessly stolen and fairly simple illustration of what this flaw looks like. It's a state machine. It has a very simple job. It validates email addresses. So it looks at these brackets and it looks at these parentheses and increments or decrements a buffer based on what it finds. Now, the essential vulnerability is that there is a pointer into a copy buffer that is not decremented when you receive an opening parenthesis. You can go back and read papers upon papers upon papers about crackaddr. It's not really important for me to discuss everything about it right now. But the point is that out of the massive amount of state encoded into this program, there is one input that causes a vulnerability. There's one input that can exploit this program, and it is incredibly difficult to find. However, the point here is that we were able to find this vulnerability. There are several systems that can now find this vulnerability post Cyber Grand Challenge because it was put up there as a test during the final event. So our CRS can find this, and it finds it through a variant of the analysis boosting I talked about on the last slide. When we actually do get all those inputs, one thing that I neglected to mention is that instead of simply minimizing the inputs, we also mix them. So if we have one valid input and another valid input, we might just cut them both in half and merge them back together again. And that mixing can eventually result in a crashing input for crackaddr. And we can reliably reproduce this behavior, not just in a lab, but we actually brought a live demo of it to the last conference that I was at. So this is something that no one really thought would be solved by this challenge, but was. So the upsides here are all the automated systems found real bugs. Total success, right? Some of the bugs were thought to be impossible, like crackaddr. The challenges. So the Cyber Grand Challenge released all of the scoring system that they used for all the different automated systems. And they put it on the internet so that other people constructing analysis tools can measure their own tools against it as well. And then some of the bugs that were found in those challenge sets were actually unknown to the authors themselves. So even when you're trying to construct a program that's maybe only 200 lines long or 1,000 lines long or 20,000 lines long for the purpose of inserting vulnerabilities, I'm sure many CTF developers understand that sometimes you unintentionally produce alternate ways to solve the challenge. And that definitely occurred, and the automated systems were smart enough to find even those bugs. So a brief aside here, these challenge sets are one of the most important outcomes, one of the most important developments from the Cyber Grand Challenge. They are 247 C and C++ network services that implement all variety of software. They are not simple tests of vulnerabilities. They are not like 10 lines of code that implement a buffer overflow. They are complex programs that implement custom network protocols and image formats and all kinds of other systems. They don't implement RFCs. There's no way you can prepare ahead of time for them. And they all have one or more exploitable crashing vulnerabilities. They're all documented. They come with CWEs, so you know exactly what vulnerability you found. They come with tests with not just valid inputs, but also crashing inputs. They come with patches, so if you're testing patch strategies, you can measure against a reference set. They come with performance measurements, so you know if you patched it, how much of an impact you had on the performance of that program. And they're all available on the internet, and we took them and ported them to Linux and Windows and Mac. Yeah? No, I mean CWE. So Common Weakness Enumeration. Yeah, so the common weakness enumerations are kind of a taxonomy of potential flaws. So you can have heap buffer overflow versus an integer overflow versus a stack buffer overflow versus type confusion and all these different kinds of things. So every single program in this data set is annotated with the CWEs that are embedded inside of it. That way, you might find a program that's incredibly good at finding type confusion bugs, and you can test it against this entire data set and measure if you found all the type confusion bugs. But then as a analysis tool user, I can demonstrate, or rather I can determine that, oh, this tool only finds type confusion. I need to augment my testing with this other tool that also finds, buffer overflows. And then with the two of them combined, I get higher coverage. That way I know what I'm finding and I know what I'm not. This is really the first data set of its kind. It's incredibly useful. We have a blog post talking about it, and it's aptly named, Your Tool Works Better Than Mine. There's a question mark there. Prove it. That's what the challenge sets are really useful for. So I highly encourage people to take a look at these and try them out on their own. They're actively developed by us at this point. We're still making them work on Windows. Not quite there yet. So the downsides here, so CGC wasn't all, roses. Most teams that build systems still require expert operation. Like I have my CRS in a GitHub repo. My team can run it. If I open sourced it, not many other people could. Still requires a lot of expert knowledge to hook up these things to real software. The usability problem was not scored in the Cyber Grand Challenge, and therefore there was no real advancement made on that front. That's fine. It's not really DARPA's concern. They care about advancing the state of research. It's on us, and it's on everyone in this room to figure it out post-challenge. The Cyber Grand Challenge was conducted inside of a custom operating system called Decree. It was made to be easier to analyze, easier to reason about, so that these competitor systems could actually find bugs. They were worried that it would be too difficult to simply throw like Firefox or something at these programs, so they lowered the bar a bit to ensure that the teams could score points. They did that with Decree, and as you can see, it's only got 6 system calls, no files, threads, or signals. So now, it's difficult to take tools that were developed for Decree, port them over to Linux, where you have hundreds of system calls, where you do have files, threads, and signals. And that's an ongoing effort for me as well. I have tools that are still custom built for Decree that I'm trying to rip out. And then there was a lot of distractions. If we had 2 straight years to focus only on bug hunting, I may have gotten farther on that one specific problem, but DARPA cared about more than that. They cared about automated patching. They cared about exploit generation. They cared about how these things fit into network appliances. They cared about deployment strategies. They cared about IDS. I don't. That's okay, you know, for them. It's okay for me. But that was somewhat frustrating for me as a competitor in this challenge. So to recap here, CGC gave a much-needed boost to the field at exactly the right time, as this was really heating up, as people were starting to think about SAGE and what kind of impacts technologies like that could have outside of Microsoft. It is now, damn it, now obvious that automated bug finding is possible and very effective. We have prototypes available. You know, you can go on the internet now and you can download entire code bases that were funded by this challenge. And the challenge sets that were created for the Cyber Grand Challenge enable me to measure my tools against yours, and we can have an honest, objective conversation about the benefits of each. So, okay, now we get into the predictive part of the keynote. Where do we go from here? What's the next step? So, these kinds of tools are going mainstream. I think about automated bug finding and smart fuzzing as where machine learning was 10 years ago. I hope that 10 years from now we are in the same exciting space as they are today. Machine learning 10 years ago didn't have a solid metric for comparing techniques against each other. Systems like SVComp came out and enabled ongoing competitions between different strategies for machine learning to help researchers make progress. And once they kind of settled on what worked and what didn't, it was then possible to start engineering solutions around a static target instead of a constantly moving one. You've seen now that Microsoft and Google, Microsoft finally actually took SAGE, allocated a team around it in order to bring it to the public, and they called it Project Springfield. You can actually sign up for their waiting list to gain access to it. Only works on Windows software at the moment, only works on binaries, still fantastic. Google has another program called OSS Fuzz, where they'll run libfuzzer in the cloud against your open source software. So these are really going mainstream. It's possible to take advantage of highly automated, hugely scalable automated systems to find bugs. My prediction is that Apple may start soon. In the CGC competition, as our internal state, we used LLVM IR. We did that because the intermediate representation of the LLVM compiler is made to be easy to reason about. It's supposed to be used by a compiler to implement various analyses for, you know, optimizing code. So it is a really great target as well for analyzing that code for bugs. Apple has most of the LLVM IR, or the bytecode, or the bitcode for all the iOS apps that it has in the App Store. And it would be trivially possible for them to analyze that code to find really basic security flaws like API misuse and privacy issues. And there's no reason they couldn't start doing this tomorrow. They don't have to roll out software, they keep it all in the cloud because you've given that bitcode to them. So they have a really good business case for this, and they have all the LLVM developers on staff. You know, they employ Chris Latner, the original author of LLVM. So I really think that we'll finally see basically, you know, most of the major technology companies using this in practice internally, and then potentially exporting some of that technology to the public. Yeah, so I explained a little bit about this. So we could automatically analyze apps for bugs, backdoors, and API misuse. There's no reason that you need to use humans or some kind of janky Perl script to, you know, assess all the applications that are coming in that need to get approved. You could reduce the time for apps to get approved and go into the App Store from like 1 week to a couple hours. And once Apple does it, everyone else probably has to do it too. You know, Google won't be able to rely on just Bouncer, where they dynamically execute the program and observe the environment. They'll likely integrate some kind of static analysis as well, and bug hunting technologies that were funded by CGC and created in this giant explosion of interest in this field. There are some roadblocks here. So I mentioned that it's really difficult to use. It's really unused tools don't find bugs. So analysis tool developers must show software devs that tools can make their lives easier. We really need to give more thought about the user experience behind these tools. They are not easier to use than Git, and Git is hard enough. We actually, at Trail of Bits, have tried to offer services around automated bug finding to our clients, and there's a lack of trust among the most savvy clients out there in this technology. We know that it works, we know the benefits that it offers, but the field that came before us is so rife with examples of programs, examples of tools that just produced millions of false positives and wasted so much time among their developers that many, even security-savvy companies, are unwilling to think about the current generation of tools. So AFL shows us the path forward here, really starting with a simple dumb tool and then slowly improving it over time is the strategy that works. And something that requires expert operation is going to die in its tracks. This funding Roadblocks as well. If you're working in this field, there's really only two places that you can get money from. You can get money from DARPA and potentially other military agencies that have an interest in this. Most people consider cybersecurity and vulnerable software to be an issue of national security. The U.S. military purchases a huge, vast amount of code that's embedded into all kinds of hardware that they use every day. There have been programs at DARPA that have studied ECUs, the computers that are inside of cars and helicopters, and the potential for those computers to be disrupted by somebody that they're at war with. So that's really kind of a national security concern, and they care immensely about finding and rooting out all of those bugs with automated means. So they'll give you money for it. Large R&D shops might give you money for it. Google might give you money for it. Microsoft might give you money for it, but they'll probably keep it all internal. So what are you to do if you're a company like mine, or you're a company that has similar ambitions to advance the state of the art in smart fuzzing and automated bug finding? How do you get paid for that? If customers are untrustworthy of the technology and the only two people you can get money from are these two. So we need to shift this. There needs to be more investment from private firms and from nonprofits especially to understand that security affects everyone. Somebody has to pay. Somebody needs to help us move the ball forward. So making that business case and finding a way to communicate it is really key to advancing the field. And then there are research roadblocks, and these are quite simple. These are probably the simplest of the three that I mentioned. So we need a realistic benchmark to show that the tools work and how they compare. The DARPA challenge sets are already almost there, and my company has taken that on as kind of a flag that we'd like to plant, something that we'd like to assist with. Bugs are getting harder, so we need to continue to improve our analysis techniques. None of the tools that we've described today can really find bugs in JavaScript engines or jitting JavaScript engines, which is where we can consider one of the most risky pieces of software for consumers today. So we need to continue to advance those techniques to find bugs. But we can't lose sight of what those techniques are capable of today. Even if we can't find bugs in a jitting JavaScript engine, we can probably find all of them in an image parser. And is it worth it to root out every single bug that's available inside of libpng? Probably yes. And I think that's a great result. And then a call to arms. When we build tools, it is no longer acceptable to build tools that simply silo themselves, that work in isolation. It is hugely important that when we construct new analysis tools, that they're capable of communicating to each other. It was a huge problem for us to try and strap all these things together into an integrated system, and that was the only way that we could make progress on any of these solutions. So if you're writing tools today, ensure that it has some kind of documented output format and some kind of documented input format that enable other people to use that tool inside of a larger system. So some predictions. I think in 2 years, we're likely going to have what DARPA calls the Centaur, which is combined human horse. Yeah. So computer-assisted program analysis. So when you're bug hunting is going to start to change over the next 2 years. Right now, you might open up your copy of Understand or your Eclipse IDE or Visual Studio, whatever it might be, and you're using or Vim and CTags, or for the insane among you, Emacs. And you might be finding bugs that way. You might be reading code from top to bottom, tracing input, using your IDE to pivot through the source code, but it's still really a manual process based on your own intuition. I think the next 2 years, we're going to start to see tools that augment that manual process with automated techniques. And a lot of those automated techniques will be adapted from the ones that I discussed in the rest of this presentation. I definitely think we're going to start to see app stores take advantage of automated bug finding techniques to help developers submit secure applications to them. It's too easy not to do. The business case is really there. The talent is in the right place for it already. It has to happen. And then these tools like Project Springfield and OSS Fuzz will remain around. People will use them in larger and larger numbers. It'll be slow, but over the next 2 years, you'll start to see the vast majority of really popular open source programs start to take advantage of continuous, ongoing, automated bug finding in the cloud. 5 years down the road, I think we'll start to see cloud IDEs where people are writing code that automatically help you create tests and automatically insert your program into a giant automated bug finding system that uses smart fuzzing on a continuous basis. It won't even be something you think about. And hopefully developers at that point will have some understanding that fuzzing is as useful to them as unit testing is. And then finally, research tools need to standardize on conventions and benchmarks, and that we'll start to see winning strategies emerge and consistent, focused competition around the development of new techniques. So, concluding this is you can take advantage of all of this today. If you're someone in the audience that's writing code or you're someone in the audience that's trying to find bugs, which I hope is everybody, you can take advantage of this. libfuzzer, I think, is really one of the unsung heroes here. AFL works great. It's very easy to use, and it's got that really nice like ASCII art status window. But libfuzzer is really a workhorse that doesn't get enough credit. For most developers, libfuzzer is actually the right decision. There's a couple of guides for how to implement that in your own code base, and I'd strongly recommend checking it out. Trail of Bits, my company, has released many tools that we used during the Cyber Grand Challenge, including the CB multi-OS that's challenge binaries, multiple operating systems. GR is our fuzzer that wraps Redemza in a dynamic binary tracing engine. Mixema is what allowed us to operate on binaries. We could take binaries, lift them back to LLVM-IR, and then use all of the LLVM-based tools on that code. And then DARPA themselves have released a vast amount of code that they use to run the challenge, including the Decree operating system, which might be fun to use. So really, in sum here, smart fuzzing is one of the most exciting and rapidly advancing fields in security. I hope that some of the things that I talked about convince all of you to take a second look at it. I'd just like to thank a couple people from my team, too, before I stop and take questions. Artem Dieneberg for really helping me a lot, put together all these slides. Peter Goodman for writing GR and for working on our Cyber Grand Challenge team. And Ryan Stortz for really leading the way at continuing to develop and maintain the challenge binaries. So that's it. Thank you guys for having me. I see I have a few minutes for questions, if anybody would like to ask any. There are 25 engineers on my team. We're globally distributed. We're based in New York. 12 of us are in New York, and the other half are all over the world. Most are in the US, but I do have people in Canada, France, and Argentina. I do internships. I absolutely do them. I do them year-round. So the way that we recruit for internships is we actually come up with the problems first, and then we recruit people that can help us solve them. So we have several things that we'd like to make advances on. For instance, we want to... Some of those subtle problems that I wanted to attack are problems that we're considering. Instead of... we're looking at advancements to AFL, for instance, proof of concepting, kind of various analysis advancements inside of AFL. We want to continue to develop the challenge binaries, make them useful. I don't know what's causing that, but continue developing the challenge binaries and make them more useful for measuring more tools against each other. We actually want to run tools on them. So for instance, actually at this very moment, not at this very moment, about 3 hours from now, a colleague of mine is in New York presenting on using the challenge binaries to measure various configurations of AFL against each other. AFL does have some different configuration switches, and there are different forks of it that have different versions. Like AFL Fast, there's an AFL for Windows, there's mainstream AFL, and then there's configurations among them. Well, if you're trying to find bugs, what's the right option? So we took the challenge binaries and ran AFL across them all with various configurations to see when they found bugs, how much processing power we needed to find bugs, to see if there were differences in the bugs that were found, like if one configuration, again, like found all the type confusion, and one bug's found CWEs of a different type. So I'd like interns to work on that as well. It's a pretty wide set, but we do them in the winter, we do them in the spring and the fall and the summer, we do them year round, and people work remote, and we have a Slack, and like everybody just mobs on problems. It's fun. Yeah, sorry for the pitch. Didn't mean to do that, but you put me on the spot. There's a blog post about that, actually, if you scroll back about 3 blog posts on our blog. Anybody else? Okay, well, I'll be around all day. You guys can follow me on Twitter and harass me there if you feel like it. It must be if I step like this way. But if you want to keep up to date on this stuff, my company cares about it deeply, and we try to spread the knowledge that we have through blog posts and tweets. So if you really want to keep up on it, just keep up with what we're doing, and I'm sure you'll follow along. Thanks, everyone.